Hello everyone, this is Dr. Zach. In today's lesson, we are going to rotate figures around an axis in order to find the volume. Let's begin. So, as long as you have determined that the area of your rectangle was 2a to the fourth, and then we're able to integrate your function, notice that they are equivalent. Notice that 1/3 of the area of the rectangle is equivalent to the area of your shady region. All right, so today we are going to take different functions and spin them around an x-axis or a y-axis. So as we look at our first question, we're taking our function square root of x and we're trapping it between 0, 4, and the x-axis. So you can see that the area we are going to be spinning is demonstrated. Now we're going to take this, spin it around an axis. When you spin around an axis, draw in a spinner to represent which axis you're spinning on. The axis you're spinning will be important. Now think about what solid is being created. Take a look at the little demonstration. See if you can come up with a solid that might be represented by spinning this region around the axis. Now it is a solid, as I said. Now notice we're going to take this solid and we're going to slice it on the x-axis, just like we were doing before with our area problems, but now we're slicing to think about volume. So we're going to slice this problem along the x-axis, as you can see where we have our line drawn. And that line, what shape is going to be created once we look at that slice. Now what I'm hoping that you see is that we are creating circles, lots of circles when we cut on the x-axis. Now what is the radius of the shape? Now the radius is actually the height of the line to where we are spinning. So in this particular problem, that would be f of x. Now the area has the shape of a circle, and so we know that we have pi r squared is the area, but the radius, as we said, is going to be f of x. So the area of our shape is pi f of x. But then I want the volume. So if we take an area and we multiply it by the thickness of the slice, then we would have a volume. But the thickness of each slice on the x-axis is dx. So the volume of a single slice is pi times the height, and that is squared, multiplied by your dx. So the volume of one slice, as you can see, would just be pi multiplied by whichever x value you're sitting at, and then your delta x sub k. Now imagine if we chop these into an infinite number of slices, then the sum of all of those slices where your k equals 0, this goes 1 to infinity, of pi f of ck quantity squared, and then delta x. And what you should recognize is that we are looking at an integral. So what we know is that if we had the volume, that's going to be equal to the integral from a to b, pi times that function f of x squared dx, where f of x is equal to the radius and dx is the thickness of each slice. So in particular, the volume of this problem is going to be the pi times the integral from 0 to 4. The function we're playing with is the square root of x. We'll square it, dx, find the antiderivative, and you will get your pi over 2 x squared evaluated from 0 to 4, or 8 pi. So for our second question, we're going to take x equals y squared and revolve it about our y-axis. So we're going to draw the symbol for spinning around the y-axis. This is very important to draw the symbol. We're going to be going trapped between y is 0 and y is 2, notice the region that we are spinning. So as you're looking at that region, can you figure out what solid is being created as you imagine that piece spinning around the y-axis? So we're going to slice this solid perpendicular to the y-axis because that's the way we're spinning it. And as we slice it perpendicular, I want you to think, what is the radius of the solid at that slice? And what you should see is that the radius has a length of x, but what does x equal? That's going to be our y squared. So the radius is y squared. Now the area of our shape, because the shapes are actually circles that are being created again, and the area of a circle is pi r squared. So then for our particular problem, we're going to have pi times the y squared squared, or pi y to the fourth. So the volume of one slice is going to be pi y to the fourth multiplied by the thickness. But what's the thickness? That's where your delta y is coming from. So we've got thickness delta y. Now imagine once again that we have chopped up an infinite number of slices. So we're going to take this as k goes to 1 from 1 to infinity, or the limit as k goes to infinity. You have the area, which is your pi y to the fourth, multiplied by the thickness of each one, and this would be your delta y sub k, and each one of these values is going to be evaluated. All right, and as the limit goes to infinity, we know that that is the definition of an antiderivative. So we're going to use the endpoint c to d times your pi multiplied by the function with respect to y, which is g of y. It's going to be squared because that's the radius, dy. Now in particular, our problem, the volume is going to be equal to pi, the integral from 0 to 2, times the y to the fourth dy. When you integrate, you'll get pi y to the fifth over 5 from 0 to 2, which gives you 32 pi over 5. So the method we're using in order to find volume is called the disk method. And the disk method, if you're spinning on x, you're going to use x values. The formula is going to be your pi r squared, since we are creating circles or disks. If you're spinning on y, or something parallel to the y, you're going to use y values in your equation. Once again, it's pi r squared, and then you're going to multiply by the thickness. So the radius should be perpendicular to the x-axis. You're going to use dx's. And the volume is going to be the integral pi r of x quantity squared, it should be r of x quantity squared, dx from a to b. For the disk method rotating on the y-axis, the radius perpendicular to the y-axis, use dy, use y values. This should be the quantity radius squared. So the volume is pi integral from c to d, radius with respect to y, quantity squared, dy. All right, so for number 1, we are spinning on the x-axis. We're going to take the function f of x, and once again, you should always draw the picture as you begin. We're going to put 0 to pi. Understand which area we're going to rotate, draw the axis for which you're rotating, and draw a representation for the radius of your function. Now the radius in this function is top minus bottom, so that's with respect to x because we're cutting on the x-axis. The radius is the function itself, the square root sine of x. Volume is equal to pi r squared, so we have the integral. Our endpoints are 0 to pi, take your radius, which is your square root, sine of x, and square it. But we need to multiply by the thickness, so it's the integral of area dx is volume. We're going to end up with negative cosine x evaluated from 0 to pi. Don't forget we had a pi in front of it, and that'll give us negative pi times the cosine of pi, which is negative 1, and the cosine of 0, which is going to be positive 1. And when we subtract, we're going to end up with a 2 pi. So for example 2, we want to determine the volume of the figure y equals x cubed, and we're going to spin about the y-axis this time. Draw the spinner. We're going to go with trapping it from the y-axis. Go. Y equals 1 and y equals 8. Now, the radius. The radius is going to come off of the axis of revolution. We want to know how long this is. Let's draw it to where the axis goes to the shaded region. What you should notice is that this one is right minus left. So the radius is with respect to y in our problem. And in this case, it's going to be equal to, we have to solve. So x is equal to y to the 1/3 power. So the radius is y to the 1/3 power. The volume, pi, radius squared, so that's y to the 2/3, times the thickness, there's your dy, and we're going to integrate from 1 to 8. And once we integrate, we will be left with our pi, y to the 5/3 times 3/5, substituting in 8 and 1, do your subtraction, you should end up with 93/5 pi. So the volume is pi r squared multiplied by the thickness. Notice for our third example, we're still using the same figure, y equals x to the third. This time, though, we have different boundaries. X is going to be equal to 0. We have x is equal to 2. And we also have y equals -3 as the place that we are spinning. Now, remember what I said. You will start on the axis that you're spinning, draw it to the outer edge, and then figure out what the radius is. So what you can see is that the radius this time is with respect to x. And the radius has a top minus bottom going on. Here's the top part of the function. Here's the bottom. So if I want to find the radius, we want to take the higher function, which is x cubed, and we want to subtract the lower function, which was y equals -3. So the radius is actually a lot different in this problem. The radius is the quantity x cubed plus 3. So when I write my volume equation, which uses the concept pi r squared, here's pi, radius was x cubed plus 3, that's going to be squared. The thickness for each one of the circles being cut is dx, and we're going to integrate from 0 to 2. Now I'm going to suggest you use your calculator for this, but you have a fraction button on your calculator that you can write your answer as 4/22/7 multiplied by pi. So that one was a little bit trickier because the radius was not 0 for the x or y axis. So let's check out example 4. This time we're spinning the secant function. The secant function is one that you're quite capable of graphing. There we go. We're trapping the secant function, y equals 0, that's the x-axis, and we're going to go from x equals 0 to pi over 3. So this is our region. Okay, but where are we spinning? We're spinning about y equals 4, which is way up here somewhere. And what are we going to do now? Remember what I said. We want to take this region and know the radius. If I draw the radius to this edge right there, there's no area in that space, is there? But if I draw the radius from where we're spinning to the outer edge, There's definitely a space, but it just looks like a rectangle. So this one is a little different than the other ones. This is called a washer method. We have a hollow piece. Think about what's going on with a circle. You have your outer part of the circle, and then you have an inner piece that is hollow. And we need to take the area of the bigger piece and subtract out the area of the smaller piece. All right, so that means we have an inner radius and an outer radius. Let's call the outer radius the big R of square because it's got the bigger region. The outer radius in this problem is going to go from where we're spinning to the outer edge. And that length, because y equals 4, is just going to be 4. Now the inner radius is smaller, so let's give it little r of x, and that length is going to be 4 minus that red curve, which is your secant x. So the volume in this problem is going to be the pi integral of our larger radius, big R of x. Remember that squared dx. We're going to integrate from 0 to pi over 3. But then we're going to subtract off pi integral of little r of x, and that one's going to be squared dx as well. So put it all together. This is pi times the integral from 0 to pi over 3, big R squared, so that's 4 squared, minus little r squared, which is 4 minus secant x, quantity squared. And don't forget, these all have a thickness of dx. Now, I would expect you to use a calculator to solve this. You come up with 8.804 pi. All right, once again, you are expected to be excellent at graphing. So we're going to graph x squared plus 1. We just need sketches. They don't have to be fabulous. Then if we have negative x plus 3 and draw that one. There we go. So you can see that the region that we're trapping, not hard to find, there we go. And we're spinning about the x-axis. So here's my x-axis and I'm spinning. As you can see, if I'm going to draw from where I'm spinning to the outer edge, there is another hollow piece in the problem. So big R of x is going to be the line negative x plus 3 because that's higher than the next part. So the next part is drawn from where you're spinning to the lower edge. So little r of x is going to be equal to your x squared plus 1. Now the volume is pi. In this case, we want to find the integral from, I need to know where they intersect. So x squared plus 1 is set equal to negative x plus 3. Once you solve it, you find out that your x's are going to be equal to negative 2 and x is equal to 1. So we're going to integrate from negative 2 to 1. Big R squared minus little r of x squared, and these are x values. Dx, make sure you use a bracket or extra set of parentheses to represent what's happening. So we're going to go from negative 2 to 1, quantity negative x plus 3 squared minus, because we want to take away that hollow piece, x squared plus 1 squared multiplied by the thickness dx. And once you finish this problem, you should end up with 117 over 5 pi. The next two examples are slightly different, so bear with me. Once again, we have to plot our graphs. It's just sketches once again. So we have y equals x squared. We know that the y-axis is a boundary this time, as is the line y equals 1. There we go. And we're spinning about x equals 3/2. So I'm going to draw that in a different color, your choice. I'm going to put 3/2 as a blue one. All right, now we want to spin about that line, and if we were to try to draw top minus bottom and right minus left, remember we got to go from where we are spinning. We're spinning on that blue line. So let's think about where we are going to be spinning this area. So we have our area. We're going to spin on x equals 3 over 2. And we want to take from where we're spinning to the outer edge. Well, how long is that? The radius with respect to y in this problem is going to be equal to 3 over 2. Now, did you notice that there's a hollow piece? That hollow piece, we're going to go from where we're spinning to the curve. Now, this was the curve y equals x squared, but I need it to be with respect to y. And we know that x is equal to y to the 1/2 power. So we're going to take the radius with respect to y, right side, which is 3/2, minus the left side, which is the square root of y. So now, put it all together. What do we know? The volume is going to be equal to pi integral outer radius, oops, should have used a little r there, which is going to be 3/2 squared minus the inner radius, which is 3/2 minus y to the 1/2 quantity squared. And all of this needs to be multiplied by the thickness of each circle. And we are integrating with y values from 0 to 1. Now, of course, you want to use your calculator to integrate this, and that works for me. All right, our last example, number 7. It doesn't look that different. We have y equals x squared again. Looks like I'm obsessed with that. Sketch a graph, got it. This time, we have 4x minus x by factor x, and left with x minus 4. I know that my second graph is going to have 0, 0. Then it's going to cross at 4, and it's upside down. So it's going to look something like this. We know that x equals 0 is a boundary, and x equals 2 is also going to be a boundary. That might be where they intersect, but I'm not sure. Let's find out. So we said x squared equal to 4x minus x squared. So 2x squared minus 4x is 0, and we definitely have a boundary at x equals 2. All right, so that's the region. But where are we spinning? We're spinning on the y equals 6, which is way up here. There we go. Definitely going to have some hollow pieces. Draw my spinning. Now the reason, once again, that we're drawing where we're spinning is so that we know to start the radius, go to the outer edge. Now this is an x value since I'm cutting perpendicular to the x-axis. The radius with respect to x, this is the longer line, is going to be equal to 6, there's your top, minus the bottom, which is x squared. Then we want the inner radius for the hollow piece, and that's going to start at 6 again. So r of x is going to be 6 minus the graph that's upside down, so 4x minus x squared. All right, so we have big R of x, we have little r of x. The volume is going to be equal to pi integral from 0 to 2, quantity big R of x, so that's 6 minus x squared squared minus little r of x, which will be 6 minus the quantity 4x minus x squared, and all of that squared. Don't forget dx. Use a calculator to integrate. Make certain you know how to use your math fraction button on your calculator. And I like to see pi in a problem, but that's up to you. All right, so you have lots of examples, and it's time for you to do some practice. As you practice, what I want you to do, number 1, is I want you to draw the graph. Make certain that you will put on a spinner so that you know how to draw the radius. Now, when you draw the radius, check to see if you have any hollow pieces so that you know if you're using big R squared minus little r squared or just big R squared, one of those two. So find the graph, spinner, draw a radius, write your integral, and then of course integrate. You may use a calculator. All right, that's it. Make certain you get some practice. Work for about 30 minutes on the practice, and then go ahead and start your follow-up assignment. Have a great day. This is the follow-up assignment.